Okay, well, thank you for the invitation. Let me start by congratulating Akshay on his Fields Medal. And it's a long time since the day that a 13-year-old boy walked into my office and out of nowhere and told me he'd looked at a paper of mine, and I didn't quite know what was going on, but we were just discussing it. He tells me he was on a family trip to Atlanta and had stopped by the University of Georgia to say hello to a couple of people. So yeah, obviously actually went from strength to strength from that moment onwards. And here we are. Who would have guessed? I guess that was about 93, 94? So a mere 28 years ago. Okay, so what I want to talk about is proof and how mathematicians view proof. And I want to do that not in a fantasy way, but in a reality way. So by fantasy, I mean, well, a lot of people here, not quite everybody, did an undergraduate degree in mathematics, and one's taught a certain structure as to building on axioms and how we have a structure that's so safe and holds up our theorems securely in place. And that is the fantasy that we get. I wrote this in the abstract as a first-year undergraduate or second-year undergraduate, and it's beautiful. I mean, it's the vision. It's just a lovely vision. I mean, gosh, it sort of adds color to mathematics. It makes you think there's more to it than these calculations you did in high school. So it's a very appealing vision of what proof is and how mathematics is structured. And you know, at least I lived with that for a long time, but gradually you become part of community, and what is proof and what is accepted to be proof seems to change a bit. So I want to talk about that. I'm really going to talk about proof, what is accepted as proof, with some discussion of what's happened with lean and other systems, and what Tim was talking about also. But I'm going to really try and focus on, for many of you, everything I say is probably very well known, but perhaps not everybody. So I guess the first question is, how do we affirm truth as scientists? And yeah, I mean, this question of objectivity came up in the last talk from Rodrigo, pointed out, and others. And perhaps I prefer to say, how do we affirm what we perceive to be true? Well, basically the game is we make assertions we believe are true, and we want to back that up somehow. So an experimental scientist create a hypothesis, and to confirm or deny, they test it, see how well the truth matches the data, and you see that all over. To some extent, even theoretical. I mean, theoretical physicists create new particles, and part of a game of creating new particles is you got to say how you can show it doesn't exist or does exist, right? Otherwise, there's no point in creating this particle or saying it might exist. For us, there's a different way that we affirm truth, and that's proof, that we need a series of ironclad logical deductions which make our claims incontrovertible. So that's sort of the thing we grew up as mathematicians learning. It is true in both cases that we have a basis of already believed truths, and we fit the new knowledge that we claim we're creating into context. And for us, we feel it's a very solid basis. These are proof things. For experimental scientists, it may be a little different, but it's still, there are believed and shared belief in certain truths. And yeah, I wanted to highlight, I guess I'll try and push this. Yeah, try and highlight that statement. What does that really mean? A series of ironclad logical deductions that make the claim incontrovertible. So we're going to ask, what's a proof, and can it be incontrovertible? So the first question is, who says the proof's correct? So there's this nice idea in theoretical computer science of the impartial observer who impartially agrees your proof is correct, right? And they can, in mathematics, it's not often used as a concept, but we do have this, that somehow there's somebody out there that we're writing for that will verify your logic is flawless, that the assertion's fully justified, and everything's good. We can ask on what basis the impartial observer goes ahead. For instance, what does the impartial observer take for granted? What knowledge do they have? How do they assert that a deduction is correct? How do they assert what needs further justification, even if they kind of believe it? I guess the whole subject of what is a proof can be obviously traced back to Aristotle and Plato. And anyway, Aristotle wrote, if understanding is to be as we posited, then it's necessary for some sort of proof. And it should depend on things which are true, primitive, and I think the primitive is a big word here, and immediate, more familiar than and prior to the conclusion, the explanation of a conclusion. So you're building on some sort of basis. And the ancient Greeks definitely recognized this as an idea. So, sorry, going back to what I just said about Aristotle, the most important thing in some sense for a mathematician, I mean, there is how do you deduce, but there's also what does primitive mean? What are these things you build on? So what are the list of fundamental assumptions, the sort of ultimate primitives that are allowed? What's what we call maxioms today? What are the sort of building blocks that one can assume and just go from there? So once you agree with Aristotle, then you have to ask, what's the point of these axioms? What are they really doing for us? And then you want to ask, what are the requirements of the axioms that we're going to build a whole structure of truth on top of? So, yeah, I mean, when you think about it, I mean, you sort of get to these things, maybe not be obvious at first sight, but you quickly get something like, you want these things to have no contradictions. You don't want to start in two different places and get two different facts. So your primitives should be consistent. And yeah, I mean, I could just have a setup which has got nothing in it. So I need a setup that hopefully will answer the life, the universe, and everything, and all the questions in between. But at the very least should be useful, should give me some hope of attacking the questions I want to attack. So that leads quickly to, sorry.
The first bullet point is sort of a definition of consistency, but the second bullet point is not a definition of consistency.
No.
Okay.
Don't look for precise definitions in this talk. Okay, I deserve it after I give you a hard time. So yeah, so how can you determine? I mean, it's a big question, right? You've got a question there, which you want to answer, but there may be a different question, which is just, could it be answered if you were clever enough? Are your axioms giving you enough? Well, are they complete enough to answer this question? That's a pretty tough question, unless you already see how to do it. Then once you've got this idea of axioms, there's a question of how do you pick them, and who picks them, and why do they pick them? So let me start with, I mean, there was a big change, as most of you know, in the 20th century, but let's go to 19th century thinking, roughly. I mean, there was a lot of debate towards the end of the 19th century, but roughly the agreed upon idea was that we know what's true. A line's a line, don't tell me something different about it. So, and then I guess it was Cantor wrote quite a bit about this, and the idea was, well, you come up against something, and then you think about what is sort of a primitive mathematical statement that will make this thing work, and means you can build a theory. So if you like, there's kind of well, I think it was he called it laws of thought, or somebody called it for him, but the sort of idea that you can meet situations and decide what the right primitive is. This led to Frege creating some axioms, and Russell finding some problems with those axioms, or in fact, to a certain extent in the language in which things were described, became a big problem, and a problem that, by the way, has never really gone away. Russell couldn't see a way to fix Frege's work, so he worked with Whitehead and tried to create a set of axioms. And they worked very hard. There's these massive volumes before they gave up, and even then they struggled with some of their axioms to find a good way to justify things. It was a really tough place they find themselves in when just going back to these very basic questions. So the big breakthrough, if you like, came with Hilbert in the 20th century. And the concept, instead of working with what you perceive to be a truth, is to say any set of decent rules and any decent language is a totally valid way to do mathematics. So you start with some set of axioms and language rules, and if you don't want a line to be a line, well, you make some definitions that give the features of a line you want, right? A bit like lean code, you create it in the way that you need it. Sorry, no, I shouldn't try and tease you while I'm talking. The great advantage of what Hilbert's proposal is it's clear what we're assuming and what we're not assuming, right? Because you just write out and you're not allowed to do anything else but those things. But the big disadvantage is, first, you don't really know what's really worth. It's not obvious what's worthwhile, but there's also a plurality. There's many different possible places to start from. Is one better than another? Is this right? Shouldn't we be trying to pick the things that are obvious and right? So, I mean, I think the view that you get from undergraduate mathematics is expressed nicely in this quote from Mel Nathanson, that we have a naive belief in truth. We prove theorems that are deduced from axioms. Each line in the proof is a simple consequence of the previous lines of the proof, or previous proof theorems, and our conclusions are true unconditionally and eternally. Yes, rather nice, beautiful viewpoint. So all theorems are provable from proper axioms. We just have to find those proofs. So so Gödel, who's instrumental in a lot of ideas in this sort of area, wrote in 1961, the truth of the axioms from which mathematics starts out can't be justified. Well, you take a particular set of axioms, and therefore the drawing of consequences is a game with symbols according to certain rules, not insights. So that's sort of a criticism. It's a little bit taken out of context, to be fair to Gödel, but it's a valid criticism of the setup of Hilbert's rules. So you can ask, what's the point of all this anyway? Should we really need to allow all these axiomatic systems? Surely there is sort of one truth. So even if we, for purposes of sort of logic and having a nice structure to build on, accept what Hilbert says, shouldn't we nonetheless be trying to pick them right? That reflects reality? Or at the very least, is there a best system in practice? I mean, can't we always decide if there's a sort of plurality issue that it appears one can go in two directions, can't we just make the right choice? So there's a very famous example, which I'll describe, many of you I'm sure know very well. So Cantor was the first to it was beautiful proof that there's far more numbers on the real line than there are rational numbers on the real line or counting numbers. So it's this famous diagonalization argument. So there's at least two types of infinity. One is the way you count, and another one is the number of real numbers between 0 and 1. There's at least those two types of zeros, two types of infinity, and then the obvious question that Cantor asked is, could there be an infinity in between, or surely there isn't? Are these the only two types of infinity? What's going on? So the intuition, I think Cantor had was, no, there's no infinity in between, and Gödel in 1940 showed that that's consistent with the standard axioms, ZFC type axioms, whatever those are, but let's just say there are a standard set of places we start off from. And okay, good, so there's no infinity in between, because it's consistent, but then rather frustratingly, we never had the Fields Medal Symposium on this particular work of Cohen, but his Fields Medal was based on showing yes is also consistent. So that's a problem. Which one do you choose? Which one is right? Which one's correct? And the answer is it depends where you start from. Right? And they're both perfectly valid places to start. You can start with no as an axiom, or something that leads to no as an axiom, and you can start with yes as an axiom, or something that leads to yes. So yeah, that's a problem. Plurality is unavoidable. Doesn't mean you can't have taste and choice, but you can't avoid the reality of plurality. So let me move on from that, but I think it's worth bringing up when we're trying to discuss what is proof and what is belief. So there was, I can't remember what it was in, but Nautilus, I think it was in. Dan Rockmore wrote a nice article, and which I'll read out. Mathematics is writing. For all the quantification it makes possible, all the technological and scientific discoveries it's helped to produce, ultimately mathematics is word upon words. There's a bedrock of definitions cross-cut by axioms whose only restrictions are that they not contradict one another. The arguments are the key, they're the proofs, without which the assertions are just so much blather. The proofs, and here's the quote I particularly like, the proofs actually conjure mathematics into existence. That it's a more controversial statement here than it might be somewhere else, given the nature of how you might prove things on a proof verification system, or how you view the big picture of the proof. But the tradition, at least in mathematical research, is it's the proofs as much or more than anything that conjure the mathematics into existence. So let me briefly talk about the Gödel crisis. So we talked about Hilbert, who wanted a set of axioms that are consistent and complete. And in 1931, Gödel horrified the mathematical world by showing that any consistent set of axioms, no matter how you choose them, cannot be complete. There are questions you can't answer using these axioms, perfectly valid ones. And it can't prove itself to be consistent. It may be consistent, but you can't work within the system to prove that. And as von Neumann put it after Gödel, there can be no rigorous justification for modern mathematics. What a crisis we're in. So one, there are true things that cannot be proved. Right? I'm not talking about, it's not complete that you can't answer all questions, but there are things at some level that are true that you can't prove within the system. So let me give you a very modern viewpoint. It actually fits in what I actually said last night. I can't remember what was the name of the guy whose theorem you talked about putting steam in one end? And Carnot's theorem. So here's Carnot's theorem in action. If you look at the set of all possible statements of a certain length, and then you look at the set of possible proofs, you have a sort of mismatch in size in a similar way to what actually I was talking about. So let me try and justify that a little bit. You can think of a statement of size n is you just take a function from all strings of length n, say in binary, okay? So just 0, 1, 0, 1 of length n. And we'll just have a function that maps every string to 0 or 1. Okay, so the simplest possible model of functions you can think of. Strings of length n in binary map to 0 or 1. So yes or no, if you like. So how many functions are there? Well, there's 2 to the n possible strings of length n, right, in binary. And they map to, each one can go to 0 or 1. So the number of possible functions is 2 to the 2 to the n. Now think about proofs. You've got a language, English, French, Lean, whatever language it is, it's got a certain number of possible letters it can use. It's got a certain alphabet. It's finite, say a gazillion. How many expressions in that language can you write of length k, say? It's a gazillion to the power k. So to be able to have a proof for all those functions, you need gazillion to the k to be greater than 2 to the 2 to the n. That means that k's got to be bigger than a constant times 2 to the n to get all the functions. That means functions of length n, the vast majority of them are going to take 2 to the n steps to resolve, algorithmically, if you like, or to have a proof of. So this is a famous argument of elementary computer science that I'm giving you, but it's sort of much worse than Gödel's theorem in practice. It means that there's tons of simple statements that you can't resolve in any reasonable period of time. So NP is basically, I mean, it's not a correct definition, but it's basically the set of mathematical statements that you can resolve in a reasonable period of time. And it's a tiny set. It's a tiny, tiny, tiny set. So I'm saying almost everything is outside of a class of things you could hope to resolve in a reasonable period of time. Okay, so we're really, I mean, beyond Gödel, the modern ideas in computer science of complexity classes really show that we're very, very limited. So how do we live with such a crisis where the theory can't be complete, it can't be consistent, you've got no hope of doing everything you wanted to? What are we even studying this subject for? I mean, and the computer's not going to do better. Well, I'll explain why the computer can't do that much better in a minute. Well, basically, most mathematicians' view of a foundational crisis is to put their head deeply in the sand. So what we do is we say, somebody else can worry about that. Jeremy can worry about that, but the rest of us, nah. You know, Akshay does his highfalutin stuff. Do you worry about these things much? Have you ever written a paper where you said, I worry if Gödel's gonna? No, right? So yeah, I mean, it's just, for most mathematicians, it's not part of your working life. I mean, you're aware of a sort of existential crisis, but am I gonna meet this? Are these really gonna get in the way? So yeah, we have a terrible attitude, really, but don't know what to do about it otherwise.
That makes it not a crisis.
Sorry?
That means it's not really a crisis.
Well, it's a crisis for some people. So.
I don't worry about it.
Okay, well, you're probably closer to worrying about it than most of us, at the very least. Yeah, I mean, okay, so like Tim Gowers has work in Ramsey theory or very close by. And there you can create statements in Ramsey theory that from ZFC can't be proved. And you know, if you look at some of those statements, if you're not an expert at least, they look pretty similar to the questions that are being answered. So you might ask, what about some of those questions people are working on? Could they possibly be over that line? But they don't seem to have a problem with it either. But it does look from a non-expert viewpoint like there are real problems in subjects like that. So the big question, to a certain extent we're talking about at this conference, is of all these issues about proof, what difference does a computer make? What can a computer do that a human can't do in particular? I think Jordi showed us some things, but let me go into this in a more sort of philosophical light. So there's a thesis of Church and Turing. It's evolved. I don't think they worked on this together, but which is paraphrased as anything sensible to compute should be more or less equivalent and universal. And I'll give you some quotes from Turing, which are rather nice on the subject. So what do I mean by universal is that what's out there to be computed, if it can be computed, a human can probably do it given enough time, right? So Williamson this morning was a bit, he didn't want to say these things couldn't be done by humans, right? He just was like, well, if you put in enough effort and you're clever enough, I think in response to a couple of questions, he basically said it could be done. Well, it's true in a theoretical sense that anything a computer do, a human can do. So, I mean, we're both what you might call, well, we can calculate anything that is calculable. So a computer can imitate a human. They can do the same operations a human can do. And part of what like Tim's talk today was, I'm not sure we understand what a human does, but we'd like to imitate it, right? So we don't disagree that we could hopefully get the computer to imitate humans. It's just a challenge how to do that. And Turing wrote in 1950 that digital computers are intended to carry out any sequence of operations that could be done by a human being. They've been constructed to mimic actions of a human computer very closely. So the net effect of a Church-Turing thesis, and indeed Turing wrote at some length, that computers can only do what humans can do, though perhaps they're faster, less prone to typos and other simple errors. Okay, so that I guess is at least one viewpoint on what computers are doing. But going back to my previous slide, they're still stuck by NP. I mean, computers got a finite size. If I took every atom in the universe to be a computer, just for the sake of argument, there's, I don't know, what the current estimate of number of atoms, 10 to the 90 or something. It's a finite number. How fast are the computers going to work? Faster than the speed of light? Let's make that the limit. What distance do you need an impulse to move for it to be meaningful? Maybe the width of an atom or something, I don't know. But everything's a finite number. So there are finite restrictions on what a computer can do. It's just not infinite. So the Gödel crisis is absolutely not resolved by any computing. It's exactly there. There's just no change. It's the same issues are there for a computer. So let's talk about human proofs, and then I want to talk a bit about computer proofs. In Akshay's oft-quoted article, he wrote that a proof is understood to mean an argument compelling consensus. It should induce agreement about its validity without any need for replication. But who does the agreeing, actually? So that's a good question. Who's the consensus? And de Toffoli, who's a mathematical philosopher, she wrote that sharing mathematical arguments is a necessary condition of mathematical justification. So so if that's true, what do we gain by sharing? Okay, so why is that necessary? What is it we gain from it? And there's this nice quote back from 1739 from David Hume, that no mathematician is so expert as to place entire confidence in his or her proof immediately upon its discovery. Every time he runs over his proofs, his confidence increases, but still more by the approval of his friends, and is raised to its utmost perfection by the universal assent and applause of a learned world. Yeah, I kind of feel that's exactly how I feel, actually. I mean, once people like your proof and think it's good, that's the best, right? And then you actually believe it yourself. Because I don't know about you, I have moderate confidence at times in some steps. So confidence in a proof stems from robustness under inquiry, that questions are asked. You can try and find a way to answer them. You need it to be competent, interested peers, and to a certain extent, you want to focus on the right points as well, right? So, I remember, I mean, it's not popular now, but a few years ago, there was this whole thing about checking proofs by random selection of points in the proof to verify, right? And that struck me as just wrong. I mean, you got to have a way of identifying the real points that are interesting. So Eugenia Cheng, who's now, I guess, better known as an artist in mathematics, but she wrote some interesting philosophy a few years ago. What is the purpose of writing a paper? It's to turn the author's beliefs via a proof into a believed truth of her reader. She went on to say that you can't just state a proof without plausible reasoning. You need the plausible reasoning, you need rigor and structure of the proof. That a carefully worded proof allays fear of ambiguity or misdirection, which I guess are the two big issues. So I sort of want to talk about the community of mathematicians. They expect proofs they can understand. Right? You can understand the proof, and actually, more importantly, they can use it. So the author gains from explaining her ideas, but I think it's the reader and listener that to a certain extent is important in our culture. It's the reader and listener isn't passive. She wants to understand, she wants to synthesize, she wants to use the ideas herself, she wants to increase her intuition and scope. And so a lot of good mathematics comes from trying to understand a proof, looking at it in your own way. I mean, that's also good for finding errors, right? So somebody states a proof one way and has their own sort of direction they're going in. I'm in a different direction. And I'm like, why is that true? Because in the way I think, that doesn't make sense. And that's often how proofs are found, not by people doing the same things, but people who are slightly off-center to your way of thinking. So different people get different things from a reading, and this can inspire new ideas in hitherto unforeseen directions. And I also think it helps us to have some sort of robustness to proofs, because it helps think about things from all sorts of directions. So I claim that traditional proofs in this way really do help conjure new mathematics into existence, because they give a community a chance to think of new ideas from different perspectives. So then, of course, this leads to the very good question, how is this objectively valid? Right? I mean, so you've got this community thing, it seems to be what the community wants. Is the community at any given time objective? You know, there was a community in the Western world that at one time felt the Bible was very objective. So when Galileo tried to suggest that the sun and the earth worked in a different way, there was objective evidence he was wrong. The Bible said so. Objectivity is clearly something to do with the time you're in and the place you're at. We want to believe that that's not true in mathematics, but it's hard to have a proof that we're objective, I believe. So, yeah, so de Toffoli again, she states that criteria for acceptability of rigorous proofs are not carved in stone. So for instance, she just sort of notes basic calculus changed a lot from Newton and Leibniz to Cantor and Weierstrass to the modern epsilon delta formulation. All of those were valid formulations of elementary calculus, but they were valid within sort of the paradigm of how mathematics was at the time and how we viewed proof and how we viewed the right way to think. So those things change over time. Yeah, so she said they're index to the mathematical community at a particular time. So is there an objective way to judge a proof? So I'm quoting a bit of Tom Hales about human proofs versus computer proofs. So I think I'm sort of have made the argument that these human proofs are not really objective. I mean, I think they're great, and I think they create something. They create a community. They create the ability to do things in different ways. There's a sort of a robustness to an acceptable proof when humans prove it, but none of that says, I objectively know this is true. And mistakes do slip by. So let's look at human proofs versus computer proofs. Tom Hales wrote that human proofs are written to make them easily understood by mathematicians. Routine logical steps are omitted. A lot of context is assumed on the part of the reader, right? I mean, you know, I think Andrews Wiles's proof was 200 pages, but probably it was going to be 2,000 if you wrote it out, even from a graduate course. So a lot of context was assumed in Andrews' writing. A trained mathematician can translate those intuitive arguments into a more rigorous argument. So it's not the proof. I mean, here's the important issue: it's not the proof that persuades the reader. It's the plausibility, taking the ideas and putting them into a context that's familiar. Right? That's what a proof means to us. It doesn't mean a rigorous going back to axioms. It's a contextual thing. On the contrast, we've got this concept of a formal computer proof. And in that case, the idea is every logical inference has been checked all the way back to the fundamental axioms. The intermediate logical steps are all supplied without exception. And so, for instance, Joanne was explaining beautifully how that's done with Lean. And so formal proof is less intuitive and hopefully less susceptible to logical errors. So the idea is formal proof avoids intuition as being imprecise, and only the formal steps can persuade the impartial observer, so I'm back to my impartial observer, to accept the proof, whoever that person is, to accept the proof, okay, because they can just see every step and it works. So is it true? Is the formal proof less susceptible to error? So let me be a little unfair on the formal provers and use some historical context here. So Peano wrote, imprecise ideas cannot be represented by symbols. And the deduction from that, which is what's used, is that if ideas are represented by symbols, they must be precise. Okay? So that's a logical deduction from Peano's statement, whether or not you agree with Peano's statement. But here's the thing, precise doesn't equal correct. So the question is, when you've used these logical steps and symbols, have you actually put everything that you want to say correctly into that language? Hopefully you have. But it's difficult to prove you have, right?
Assuming Peano is correct.
Yeah, I'll assume Peano is correct. Yeah.
Which I don't agree with.
Okay, good.
I mean, that symbol's right there.
Uh-huh.
But I think it's a pretty imprecise idea.
Yeah, I mean, the language is tricky. And it's very, as Dan Rockmore said in the quote, it is an integral part of proof and how we understand proof and what we believe. And there's just no escaping it. So you can be precise and wrong at the same time. So and just going back really to Hales's positive views on formal proof, we still have a question of who's the impartial observer who reads through that and says, yes, you're right. For me, translation errors are probably the most important issue because I think they come in many forms, going between human and formal language and back, formulating the question formally, interpreting the answer correctly. Yeah. So, and then the ultimate question is, really the important question, at least from my community-based view of mathematics, is at the end, will we obtain a desirable and useful proof that actually increases the sum of human knowledge? Or do we just have something that you put in a filing cabinet, you know, like all the forms I fill in for the university administration, they go in a filing cabinet, everybody forgets them. I mean, which is it? So for me, what's important is I'd like formal proofs to conjure mathematics into existence in some form. And again, I want to be fair here. We heard, I mean, just this amazing thing about the, I'll probably get the words wrong, the Breen-Deligne resolution, that by formalizing, in the process of formalizing, that wasn't the computer that did this, but it was the process of formalization made you realize that these hypotheses didn't mean you had to use this heavy machinery, right? So that's cool. But it was, again, it wasn't the formal proof that did that. It was the taking what you knew and putting it in a form that would work for the formal proof that gave you this breakthrough. Yeah. So formal proofs, so here's, I'm going to be a bit negative now. Formal proofs chase details back to axioms. They don't use a library of agreed upon knowledge. So basically, you know, what we do is, most of us professional mathematicians, we rely on theorems in other papers. So there's a library out there, right? And we don't check up on the library very much, right? We just hope by hearsay that it's been refereed, hey, it must be correct. I haven't heard anybody say it's wrong. So that's a perfectly valid library for a working mathematician. In Lean, hopefully, although you might use a library, say I'm going to use, you know, whatever, x squared plus y squared equals 1 represents the point in the circle theorem, whatever it is, that has been checked back to axioms. And I'm sure you'd say, yes, you could go and just click on it and check it. So, but my feeling with a proof like that, now maybe not the presentation, but it feels like it's like a child saying, why? And then you think, well, what does a child get from saying, why? Why can't we stop? Why can't we, you know? Aren't you just better off saying, I said so? So there's a level which formal proofs feel like that to me, in my ignorance. And it certainly doesn't help conjure mathematics into existence, saying I said so.
Can you go over the second part of your slide again? You think of Lean as a child tirelessly asking why, and then...
No, let me just say the picture presented actually by Tom Hales of a formal proof made me think that. But when there's a level at which I know facts are true, and if I formalize it and it keeps on asking me to justify these annoying little steps back and back, I mean, I personally think we get very frustrated with it. Does that make sense?
Yeah, I think so. Okay.
So the community standards don't always work, and there are famous mistakes in mathematics. So Andrew Wiles, of course, used properties of a ring in his original proof. I mean, there were lots of, I should say, by the way, that when Andrew Wiles presented his proof in '93, it was more of a plan of a proof than a proof. There were bits that he was pretty confident of, and there were bits that he was confident that probably he could fill in. So, I mean, I was there, not that I was an expert, but it was the first major conference at the Isaac Newton Institute, which is where he got his degree, right? So I think he felt like this would be a great way to kick the institute off. So, huh?
I was at the first, he was at the second.
Okay, was it the second? It was the first year, that's what I remember. Yeah, so there was this feeling of I think that he wanted to do something for his alma mater. But maybe he wasn't 100% ready when he gave this. In fact, during the lectures, there were 3 lectures, he did say a few times sort of like, I'm pretty sure this is true. I need to work it out. So it wasn't like he just claimed 100% to have everything worked out, but there were a lot of prominent experts in the room who just nodded wisely most of the time when he said, I can work this out. It was interesting. There was one point, and again, this is a community standard thing that I think is very interesting, is he used some theorem of faultings, and a professor whose name was, because I asked him if I could name him, and he said no. He said that theorem's definitely not true. And well, I was like, ooh. And then he explained what it is he needed of a theorem, and the same professor said, I'm pretty sure that is provable at this point in time. Okay, so yeah, so there's a community back and forth with a prominent proof, but actually what happened after his lectures is this sort of definition of a ring took on a life of its own. What seemed to be not a major point became a massive point, and really put him back for a year or so, I think it was. I can't remember. Can you remember how long it was, Michael?
Published manuscript arrived September, I think,
Okay, that was June 93, I guess, the conference, I think, yeah. Right, so it took him a while, and it was very painful for him. He wished he hadn't announced it publicly before he got the details right. Anyway, yes, that's a famous mistake, but in some sense, community standards also helped him. He presented to a seminar in Princeton. Famously, Nick Katz helped him find the problems. They identified them. They were very difficult to resolve, but there was a community, and of course, Andrew Wiles was very honestly wanting the proof to be correct. He wasn't defending something wrong. An interesting one has been Mochizuki, and that's actually very different in its nature, the issues of Mochizuki's proof of the ABC conjecture, or claimed proof of the ABC conjecture, because Mochizuki made a very weird choice, which was to ignore the community standards in many ways. So he decided, my proof can only be phrased in a certain very strange way that is quite different from standard algebraic geometry. And I'm only going to phrase it in that way. And if you in algebraic geometry or arithmetic geometry don't like it, that's your fault. So the general community standard is, if people don't understand your proof, you explain it some more, and hopefully you find a meeting of minds in language. But Mochizuki point blank refused to do it. And then Peter Scholze, again famously, went there. He studied the manuscript. He thought in terms of the sort of arithmetic geometry thinking he has. And he felt he'd reconstructed the argument, and he got to a point where he couldn't really understand quite a few things. I mean, he kept on kind of sort of substituting things he could prove for what Mochizuki said and felt they were equivalent, but he got to a point where there's no way he could make this leap from one lemma to the next. And he asked Mochizuki for help, and he went to Kyoto, and they argued. And anyway, but you know, at the end of the day, they ended in disagreement. Mochizuki still claiming, well, the only problem is you're not trying to understand my language. Now, in the Hilbert dream, it's not, I mean, I have to be a little bit careful because Mochizuki's not entirely starting with new axioms, etc. But in the Hilbert dream, it's perfectly valid for him to have his own language and his own way of doing things, right? As a plurality is acceptable. On the other hand, we have a community where what is the proof if your peers aren't going to agree it's true? So I think the current stage is, in some sense, by community standards, it's not true because he hasn't persuaded the prominent people in the community. There's the Vladimir Vodsky and Kapranov famous proof, which I'm not going to talk about technically because I know nothing, and there's an expert who's going to speak next. I mean, here's the interesting point. So Vodsky, I mean, I guess it's sort of, I don't know the exact details of the mistake, but I think it's to do with definitions and having a sense of what's the right way to move the subject forward rather than a big overarching theorem where the issues arose. And a very subtle mistake emerged after some time. And what was interesting was he didn't want to go out and say it publicly because he felt that by some sort of reshaping of things, right, Vodsky, that actually this theory would all fall into place beautifully, all the pegs would fall in the holes, and you'd have a wonderful theory. And it took him a while to acknowledge that that really wasn't happening, and that he really had to think again about these foundations, and thus the birth, that's my interpretation of the birth of, well, okay, you can do it better. But I think as a community standard, it's interesting because Vodsky was participating in the community standard, but on the other hand, he felt he was allowed to take his time to get it right. I guess I'm not doing brilliantly for time, so I won't go too on, but one I was personally involved in was Golson and Yilderim on short gaps between primes, which was a breakthrough in 2003 that the community accepted. And a brief version of a story is that they put out a preprint, and all of the stuff that was new in the paper was right, and it all worked, and it was very surprising, but it all worked. Very, as an expert, you read it, it was right. And there were a couple of lemmas that weren't brilliantly proved, but they were pretty standard, maybe a bit different in this context, but different, but not fully proven. One, basically, what was the phrase you used for a placeholder? Huh? You had it in your proofs. Was it meta variable? No, you had a phrase sorry. They had sorry at the bottom of lemma 2. So basically they had a arbitrary dimensional integral as you go through all the cases. They'd worked out 2 dimensions. It's a complex integral where they had to shift contours. They worked out 4 dimensions. So they were trying to see if there was something tricky when you went up a dimension, right? It was all even dimensions. And they basically said, we're pretty sure that in every dimension you can take this kind of algorithm and shift your contours and it'll work out. But they were wrong. You couldn't. It turned out it was either 8 or 10 dimensions. Their algorithm failed to work, and actually the conclusion of a lemma was wrong. So it was a very strange mistake. It got accepted by the community. And the reason I was part of this was that this was exactly the sort of thing I was interested in. I completely believed their paper. I completely believed the sorry. And then I thought, well, how do we modify the argument to do better? And with my collaborator, Soundarajan, we proved there are infinitely many pairs of primes with gaps 16 or less. And then we were like, nah, there's not enough beat in this thing. There's no way we prove this. That lemma is suspicious. And gradually we eventually found a counterexample to the lemma. So yes, that was the end of that. But what was interesting, because it was good mathematics, when Green and Tao were working on primes and arithmetic progressions, that part of the part of the algorithm that created what's called a sieve weight was actually perfect for the argument of Ben, Green, Terry, Tao. So the last step in proving their famous theorem was the Golson-Yilderim sieve weights from that paper, that wrong paper. And then subsequently, they fixed their paper, and then it was done far better with much more machinery by Yitang Zhang, and we've probably heard the story. And then Maynard and Tao did their sort of unbelievable results, even without using a lot of extra machinery. So it's interesting because the community standard, although we found the mistake in Golson-Yilderim, the ideas were great, and they led to a lot of fantastic breakthroughs. So computers and proofs, there are 3 main uses. This has been said several times at this meeting. Calculations to assist a proof, assist in verifying the logic of a given argument, computer-assisted proofs, or computer verification, and then proving new theorems like Tim Gowers was talking about earlier today. Not quite creating their own mathematics, though Tim's talk, I think, was on the verge of talking about creating their own mathematics. Yeah, so calculations establishing a proof. So I claim that we are actually so used to seeing calculations and proof, we don't even recognize it. So when somebody says, Michael writes a paper and he says, this is a modular form of weight something and level something, for me, that's a calculation. So for him, it's obvious, right? So knowing some information is based on calculations that have been done in the past. And for not all of us, that's an immediate thing. So I think there are many calculations in proofs and explanations that aren't acknowledged as calculations because they weren't done in the paper, but they're in the background. And this is all a question of how much detail is needed to be given by the author to justify a belief in whatever. So the basic consensus seems to be that if there's some novelty in the claim, then the author must produce a coherent explanation of the calculations that led them to make the claim, describing them so an interesting reader or impartial observer can repeat them independently. This is most famous in proofs of the four-color theorem, which I have to say, I'm going to really criticize the literature here, the philosophy literature. So Apple and Hay can produce a proof, which, it's a certain structure to a proof. It's about reducing to a finite number of cases, finding a way to set it up on a computer. And it was a brilliant piece of work, but that paper is overwhelming, it's messy, there are things that aren't quite correct, it's a hard read. When you do the calculations, what an independent calculation person finds isn't exactly what they claim to have found. So it's kind of a proof, but it's got issues, right? I mean, it was a great, great breakthrough. So in 1996, these four authors decided that they would rework Appel and Haken's proof, but they would make their paper completely incontrovertible. So in the sense that they wrote out, they vastly reduced the number of, still in a lot of cases, but they vastly reduced the number of cases you got to look at. And I mean, I read it in an afternoon. I mean, it was beautifully written. They very consciously made every step clear, every deduction clear, and it still was a massive calculation, but they also explained that very well. So to me, it was 100% proved. So some of the philosophy literature seems to think there's some controversy about that proof. There's no controversy. By mathematical standards, that was 100% proved. But then something very interesting happened was that one of the early proof assistants came along and repeated their proof. It's the same proof. But what I think Gontier did that was very interesting is that he decided to try and write his proof assistant with lemmas that weren't specific to this problem. So he looked at it in a slightly bigger context, especially the calculations that don't appear in the paper. So I think Gontier really did add something in his proof assistant because he did more, and he sort of did something more that gave you more information, but nonetheless, it's the same proof. It's the same cases that were worked out. Okay, but finding the proof isn't the same as verifying it. I'm not sure why I said that. Anyway, so computer error, it's obviously something you have to think about when a computer is doing proof. We know that computers never make mistakes. However, there are hardware problems. We've all seen hardware problems. One, again, I was a little bit involved in 1995, the Pentium chip was recalled. It cost Pentium $475 million to recall it. And it was actually because Thomas Nicely in Virginia was computing a number theory constant, and he got the wrong answer. And the more he redid it by different methods, he kept on getting the same wrong answer. And they basically denied, nah, there's no problem with the floating point arithmetic, but he was obstinate. And it led to them recalling it. Subsequently, we found out that they knew it was wrong, but they knew what a recall would cost them. But that's important, you see, because we use computers, and they have hardware problems. And you can't say they don't. And you can't say the computer manufacturers are honest, because they're not. They're not going to recall something that costs them a fortune. It may be the next version doesn't have that problem, but that's a different story. Of course, there are programming errors, and Thomas Hales claims it's 1 bug per 100 lines of code. Oh, and I should say that it's supposedly that very, 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 very carefully written code, like in the space program, 1 bug per 10,000 lines. That's what they estimate, but there's still errors. How important they are is a big question. So implementation errors. So understanding what the problem is fully, because there may be cases that you never thought of that arise. What do you do with that when you're programming? So Turing said it's not possible to produce a set of rules to describe what to do in every conceivable circumstances. I'm not sure he had any justification for saying it's not possible, but anyway, I like the way he talks. In a given situation, you can decide on a protocol, but it may well be there are further difficulties later. So I think the obvious thing to do to avoid difficulties is to try and repeat the same calculations, different computers, different chips, different software. And different chips is important because the Pentium problem Nicely found was in its floating point arithmetic. So different programs accessed it, could have accessed and got the same error. So you really have to go all out to do things differently. I mean, I think this is important in proof verification too. So obviously we know that verification software came along because computer scientists wanted to verify software. So in the developing software, they wanted to verify that a program did indeed what it was supposed to do. So they invented software to check the protocols and the logical flow. And such software has been useful in development of code. It makes developers much more confident, and it means that steps of the process that were previously used don't happen, so it saves Pentium and Co a lot of money. And now these same ideas are used on verifying proofs and even assisting in developing proofs, because once you identify something that's an issue, maybe you'll cut off a problem before it occurs. So on this very general subject, some famous mathematicians quotes: Stalin, I don't believe in a proof done by computer. I believe in a proof if I can understand it. Voevodsky, computer-generated proofs teach us very little. I hope you'll address that. Yeah.
In the statement by Yilderim, why does it matter that the proof was done by a computer?
Yeah. I guess his prejudice was probably any proof done by a computer he's not going to believe.
No,
Yeah.
it's longer than that.
Oh, is it? Okay. Okay, what was the point? Do you remember the point in the original quote?
There's the part that he cannot check because it's done by a computer.
Okay.
But if a computer posts something to the archive, doesn't mean we understand.
Oh, if it's something that he can read, then it doesn't matter.
Yeah, and if it's done by a human like Mochizuki and you cannot read it.
No, you're 100% correct. So the prejudice in that statement is assuming a computer is not going to produce something readable.
And humans do.
And humans do. Yeah. Okay, you're doing well here.
100,000 of lines of
Nobody is.
I think just because it's done by a computer doesn't necessarily mean I'm gonna accept it.
No, sure, fair enough.
Yeah, but I think more than that, his experience was that nothing produced by a computer that he'd seen was something he believed because there were parts missing that he wanted to check. Yeah.
I'll try to find.
Okay, thank you, thank you. So this may have changed since I got this information from somebody, that computer proofs typically produce about 100 times more details than humans. Automated provers use an almost unreadable language, though that would be disputed. The language seems to discourage intuition and motivation, the language I'm saying, but I think the process is different. So can we trust output from a proof verifier or prover if we can't or don't want to read them? And are these insurmountable obstacles? So the executive summary is that computer proofs produce too many details to be human readable. Human proofs, too few details to be computer verified. Where do we meet? In the middle? Nah. Computers have one purpose, to serve us. So computers and programs need to move towards what's useful for humans, to present things in a way that works for us. And there are other questions that, again, Tim addressed to a certain extent in his talk. Can a computer generate a proof look for why as well as how? And I guess after Tim's talk, there's sort of what does that even mean? And how are they different? What entirely constitutes a proof? What details are required? They're all good questions. Yeah, sorry, I seem to be repeating myself, I'm sorry. So the current situation, one feeling is, okay, if you have different computer verifiers, I mean, one's currently dominating the market because it's done some wholly remarkable things that, you know, I mean, I mentioned Coq had previously completely surprised us, but they're developing in different directions, doing different things. But in some sense, that's not entirely desirable. It'd be nice if they'd had different viewpoints and we're doing the same things, and then we could compare their outputs. Or even better, they could read each other's outputs. So your output could be read by Coq and see if they believe it's correct. That would make me happier. Having a community of computers.
But it's there.
How is it there?
So first of all, there are independent verifiers for lean code. So there's the lean kernel, but there are other programs that can read lean code and check that. And Coq is one of them.
Okay, well, I like Coq being one of them because it worries me if they all come from the same place that they all make the same mistake. But if they come from a different place, that's good. Yeah. So we need a community of computers that sets its own standards and referees each other. They need to work in a common language, which has been a problem, but maybe it's not so much anymore. But to a certain extent, it excludes humans. We're still just believing that this community agreeing is correct. We'll have an argument at the end. So the computer prover perhaps could learn high-level arguments. So I was very excited when Johan put up the slide with the LaTeX proof, which I misinterpreted as Lean having done. That would be great, right? If at the end of the day it produced maybe a long argument, but at least in sort of LaTeX format with nice short lemmas all the way down. So we'd like it to learn high-level arguments or produce them that humans could understand and appreciate, present its proof not only for human verification, but to help us understand. So that's another level. The proof might be like in human articles where we use acknowledged correct papers, so you use a library. So that for being person readable, that would make some sense. The prover might be able to react. At the moment, I guess the reaction has to be through somebody who's very familiar with Lean, and I mean, there is some level of interaction right now, but it would be nice to increase that, and to answer questions on variance and so forth. Yeah. It should become, well, that's, I guess, one of the major topics here. A user-friendly system should become part of a mathematician's arsenal. As I guess I'm sort of at the beginning of Akshay's vision of how does this start? That computers are really part of the mathematician's arsenal. Yeah, maybe I don't need to go through this. I think somebody did mention this thought that we misinterpret what Google Translate does. It does remarkable things, but it's not thinking. And I like to compare this, let me go back. I like to compare this to librarians. When I started as an academic, librarians were the gatekeepers of all knowledge. And people would sometimes ask librarian questions as if they knew something about your discipline. I mean, they were given superhuman powers that they didn't have because they were the gatekeepers. Now it's less obvious that Google doesn't have those powers, but it doesn't have those powers. It's just the gatekeeper to information. Okay, so Tim briefly mentioned, I mean, he's working on the second, I guess, iteration of his project with Gannis Selengem on automatic theorem prover. But the first generation paper is pretty interesting from 2014, which doesn't strip everything back to axioms, but rather tries to proceed like a human being. So most interesting to me is this idea of modeling human tactics. So I'm going to interpret tactics as a certain way that when you've got certain information in your hands, how do you proceed? And the sort of classic computer thing is you build a truth table, or like of every possibility. You got this massive tree of stuff, and then you try and snip off some of the branches so the search isn't crazy, right? And then your tactics might be how you snip off some of the branches. But a very interesting thought in their paper is, okay, you've got this combinatorial tree of different things to try. You've got this plan in place, and you discover something. You get some information. You guess something that may be relevant, a lemma that may be relevant to the eventual proof. So it gives you more information to work with. A human, given a lemma that's obviously going to be useful in the eventual proof, probably dramatically reduces the amount of things they're going to do. They're going to easily discard a lot of the possibilities. Typically, a computer searching for a proof, given more information, is going to create more branches. So one of the issues that they bring up is, so I'm saying other things, but can a computer be more like humans, that it learns from past experiences and reduces its running time from what it learns? So I eventually got to that, so I'm panicking about the time here. Okay, so that's one of the fascinating things in their paper, that they're attempting to structure their proof-creating program differently so that it's a little bit more like humans. And also, I'm sorry, so the other thing which I ran over, didn't go through, is just that the input and output should be generally understandable. It should be in a language that feels compatible with humans. So they focus to a certain extent on the imitation game. So the imitation game is that you want your computer proof to look like it's a human proof, okay? So a game I like to call machine versus Terry Tao. So yeah, so you've got a tough, doable question, and they each resolve it, they each find a proof, and the question is, can you say whose proof is who? Yeah, so the imitation game is a party game in pre-war England where, what is it, a woman, I can't remember the thing now, but there are two participants, and they both pretend to be her, and the person has to, so they pass messages, I guess, on little pieces of paper, the two participants, one a woman and one a man, and the person who doesn't see them has to guess from their answers to questions on little pieces of paper which is the woman and which is the man. So, can the man perfectly imitate being a woman? I think is the original imitation game. Okay, so in this case, an interrogator tries to distinguish via e-communication between Terry Tao, who tries to prove he's a human, and a computer who tries to fool the interrogator into believing it is human. It's a Turing test. Turing's view is, since computers are universal, they will eventually perfectly imitate anything, humans, each other, aliens, Terry Tao. So it's a question of when, not if. So Ganassalangam and Gower selected problems to prove and got thousands of independent readers to try to distinguish between proofs by their program and proofs by real people. And the results were encouraging. It wasn't a disaster. So I think that's sort of where they left it. Oh, that a lot of people couldn't tell the difference, essentially. Yeah. Okay, so Alpha 0, well, we've heard about that. It was switched on. It learned, it worked things out for itself. It became Grandmaster in chess, Go, and Shogi, whatever Shogi is, I don't know, but it learned all three. Absolutely superhuman. So it created its own tactics and strategy. One Grandmaster defined its play as alien, that it did some sacrifices that no human would ever dream of. Yeah, obviously, there's this question that Geordie Williamson talked about to a certain extent today about can this reinforcement learning lead to greater depth and variety of mathematical proofs? Could it create proofs that are surprising, that go outside the box or the convex hull of previous ideas? Can it make the difference? Like I was trying to ask Tim Gowers, can it sort of link two areas that couldn't be linked? Can it conjure mathematics into existence? So there was a preprint recently that was very disappointing, I thought. They finally put out a paper called Alpha Tensor a week or two ago, which is basically multiply two matrices. The question is, take two matrices, say 6 by 19 and 19 by 47, and how many multiplications do you need in the action of multiplying two matrices together? What's not difficult is with 2 by 2 matrices, you've got the first row times the first column, there's 2 multiplications and addition, and there's 4 of those, so there's 8 multiplications in the traditional multiplying 2 matrices together, but Strassen got it down to 7. So, and then you can scale it up because you can break bigger matrices up into 2 by 2 blocks. So you get a bit of an n-squared algorithm, you get a, whatever, n to the log 7 over log 8 or something algorithm. 2 log 7 over log 8. But anyway, so the question is, you know, what in general, what's the most efficient way to multiply together 2 matrices? And Alpha Tensor went ahead, played some games. I don't know how they defined it. And they put out this paper, which has a lot of telling you how great it is. But in Nature, the editorial policy was dreadful. But from what I can understand, it's improved 20 cases. So there's no general theorem. There's no, when I multiply A by B and B by C, I get, you know, a new theory. What they've got is certain cases, they've reduced the number of multiplications. I noticed it was never more than 5%. There's certainly no new general theorems other than just using Strassen's methods. So a little disappointing. I mean, what it feels to me like what people do in mathematics of computation. You find new examples, you have better techniques. So obviously, it's probably got more power than any human can dream of. But it's how far in front of humans will it be? I mean, this is actually a perfect example for criticizing them because they've got a little bit better with all that power. Can they really do a lot better than humans? Oh, things like, yeah, 3 by 5, 5 by 7, but yeah. Yeah, I don't know that it helps us think up provable generalizations. I thought Geordie would contradict me and tell me, no, you're wrong, but he didn't when I asked the question. Maybe I don't know if I should talk about the Peter Schulze using lean. Unsure about his complicated proof with Golson. He worked with the lean team to interactively verify and correct his proof. He wrote that interactions with the lean team, or actually he wrote to me, I asked him specifically this question. The interactions with the lean team convinced me that a proper verification was going on. If I had simply got the response that everything's correct, I would have been extremely suspicious, as I'm sure I made slips. Confidence came, it's correct, came from seeing Lean run into all the nasty little details I'd expect, and some I'd even not expected. So Johan told us all about that. He felt the whole experience was a genuine human experience, similar to going through this for careful calling. In fact, he named Ofagaba. Johan's, the proof simplified by understanding what's needed from homotopy theory, simplified what he'd done, and by reworking proofs to be inputable, simplified some of the things going on. Tom Bloom, who's in my field, similarly formalized the proof of a very nice theorem he'd proved, and I talked to him a few weeks ago, and his experiences were very similar. He, by putting it in the format, he learned quite a bit. So the interactive proof did help conjure mathematics into existence. So the future of proof, so raw computer power obviously extends our capacities in significant ways. And as Kevin Buzzard writes frequently, or says frequently, the more people play with Lean, the sooner interesting things are going to happen, which is fair enough. Proof by computer might be very different one day from what we know. As Akshay said in his essay, this will enhance our ability to do mathematics and may well, oh, sorry, you said will, I won't paraphrase you, will alter our understanding of what mathematics is. So we can only guess what mathematics will be conjured into existence. Okay, that's it. Sorry, it's quite so late.